Let's consider how to go from a state n to a state n prime for the harmonic oscillator. Okay. Well, I mean, we can do this because we've now come up with a raising operator and a lowering operator. So let's say, for the sake of argument, that I want to lower n down to n prime. And then I want to figure out what's the probability that's going to happen. What's the probability that I'm going to go from an n state down to an n prime state? Well, mathematically, the way that's written is that I say I operate with the lowering operator on the state n, and after I do that, I want to make the product of the state n prime, and then from there, the product should tell me which should be related. I could then square it and get the probability from there. So, okay, so let's work this out. So if I lower n, so that means I have a factor of the square root of n, and I now have a state n minus 1. And so I can take the square root of n out front, and now I have n prime, the product with the state n minus 1. And since these states in the harmonic oscillator are orthogonal to each other, then this is only going to be 1 if n prime and n minus 1 are the same thing. So I basically can write it succinctly as the Kronecker delta. So now, if n prime is equal to n minus 1, then I would get a value of 1 for the delta function, and then I would just get the square root of n. And then I would square it, and I would get a probability of related to n squared. Likewise, if I wanted to raise something up, so I would take the raising operator and apply it to n. That's going to raise up. So I get a factor of the square root of n plus 1. Sorry, that's a little messy. I get a factor of the square root of n plus 1, and I've now moved to the state n plus 1. I can factor out the square root of n plus 1, and I now have the projection of n plus 1 onto the state n prime, and that's only going to be non-zero if n prime is the same thing as n plus 1. Okay. So why is this useful? Well, if you think about it, we can actually write this down as kind of a map. We could write it down as a matrix almost, where if I'm going to be raising up a state, so a dagger, then I could write down the states n that I'm starting with, and write down the states n prime that I'm going to end with. And those states are 0, 1, 2, 3, dot, 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 dot. Or n prime is 0, 1, 2, 3, dot, dot, dot. So I can now write this as a grid. And so raising up 0 raises it to a 1. So 0, 0 is 0. Raising up a 1 and would not raise it up to the state 0, so that would be 0. So basically this first row is just zeros, because I can't raise a higher number to a lower number. I can raise a 0 to 1, and the factor would be the square root of 1, because I've gone from 0 plus 1, so it's the square root of 1. I can't raise a 0 to a 2 in one step, so that's 0. I can't raise a 0 to a 3 in one step, so that's 0. I can't raise a 1 to a 1, so that's 0. And again, I can't raise a bigger number to a smaller number. I can raise a 1 to a 2, and that would be a factor of the square root of 2. And that's 0, dot, dot, dot. This would be all zeros now. And then I would have raise a 2 to a 3, so that would be the square root of 3. And this would be 0, and so forth and so on. So now I've got this matrix, really, where showing you what the factor is if you want to go from a state, say, energy state 2 to the energy state 3. I would just have to multiply that factor by the square root of 3.